This is Precalculus Chapter 13, Lesson 3, Basic Probability. All right. So, with probability, information about the population as a whole is used to draw conclusions about a sample. It's just the inverse of statistics. With statistics, we go from the sample to the population. With probability, we go from the population to the sample. All right. So there's some terminology you need to know with probability. There's the experiment, right? You always have an experiment, like rolling dice, drawing cards, right? That kind of thing. There is also the sample space. All right, so this is my population, right? This is my population. The sample space is all the possible outcomes. So the possible outcomes are a 9 of hearts, a queen of hearts, a 2 of spades, a 6 of hearts, a king of diamonds, and a 10 of clubs. That's my sample space, right? All of the possible outcomes. All of them, all right? So what is probability? Probability is, and I'll write this on the board. I don't know if this is in your book anywhere. But probability actually is the probability that an event will occur is whatever the favorable outcome that I'm looking for is, favorable outcome over, that was a pretty fussy marker, over all the possible outcomes. All the possible outcomes. Okay, so back to our cards. I should have picked 2 cards that were the same, but I didn't. Okay. So all the possible outcomes for these cards, how many are there? Well, first of all, we did my sample space. But all the possible outcomes are 6, right? So 6 would be my total possible outcomes. And I could say, what is the probability of drawing a king? Well, there's only one of them, right? So in this sample space. So it'd be 1 out of 6. But if I asked, what is the probability of drawing a red card? It would be 4 out of 6, right? Because there are 4 red cards. So that would be the favorable outcome, right? 4 out of 6, you would simplify that to 2/3, okay? So the probability of an event occurring always will range from 0 to 1. It'll never be below 0. It'll never be higher than 1. Because what if I asked, what is the probability from these cards to draw a 3 of diamonds? 0, right? So probability means that it never happens, right? The outcome never happens. Or it can be that it always happens, right? Like if this were my sample space, right? What's the probability that I'm going to draw a king? 1, right? 4 out of 4 or 1, right? All right, so it can always happen or it can never happen or it can be anywhere in between, all right? Now, all right, let's go back to these cards. Okay, we said the probability of drawing a red card was 4 out of 6, or 2/3. So the complement of that, this is the complement, like we have complementary angles, we have complementary probability, okay? The complement to that would be, what is the probability that I don't draw a red card? 2 out of 6, or 1/3, right? So that the probability, the complement is always equal to 1 minus the probability of the event. Always. The complement is always 1 minus the probability of that event happening. All right, so look at example 1. We're just going to walk through it. Some of this terminology is in there, okay? All right. So with example 1, it says suppose that 100 marbles are placed in the bag. What is the 100 marbles? The 100 marbles is my sample space. It's my sample space, right? The 100 marbles is all of the sample space, all right? And here I have 50 red, 30 blue, 10 yellow, and 10 green. All right, so we answered A, our sample space, all right? Then it wants us to write out a probability distribution for this experiment. All right, so we can. We're going to say this is color, and this is probability of that. I'll put probability of that color. Probability of C. All right, so we have red, we have blue, we have yellow, we have green. This table is going to be important because then we're going to look at this in a little bit. All right. Now, what's the probability that we get a red? 50%. So it can be written in percents or fractions, right? I'm going to write 1/2 because it's 50 out of 100. What about blue?
No.
3/10. What about yellow? 1/10. What about green? 1/10. Okay, I'm actually going to write that as 5/10 below here just so you can see a point. The sum of these probabilities should always equal 1 because all the options are covered, okay? So if we add in 5, 3, 1, 1 over 10, it equals 1. The sum of the probabilities will always equal 1. Okay, the next question actually gets into something that is taught later, all right? That is just below it, actually, all right? And so this asks, look at question C. What is the probability that a blue or a green marble will be drawn? Those are called mutually exclusive events. A mutually exclusive event is an event that has no outcomes that are alike. Like I can't reach in and choose both of them, right? But what if I asked what is the probability of choosing a red card or a king? That's not mutually exclusive because I can pull a red king. Do you see the difference? Right? All right. So with mutually exclusive events, you're always adding. Okay, and we're going to explain that a little more. So with mutually exclusive events, you're always adding. Okay, that's important. Because with independent events, you're multiplying. All right? So mutually exclusive events is like when I have one draw and there's no outcome in common. Either I am going to pull I forgot what the colors were, blue or green. So that would be 4/10. You would add them, 3/10 and 1/10, 4/10, and you'd simplify that. Okay? Now, see, then it gets to mutually exclusive events. Why would they, anyway. All right, so mutually exclusive events. They're like disjunctions, like they go in opposite directions, right? It's when they both cannot be true, like the king and the red card, right? They both cannot be true. And I've written some of these things in the book, like turning left or right. You can't turn both left and right, can you? That's mutually exclusive. Right, don't do that. One toss of a coin, right? I'm only going to get either heads or tails. That's the only options. Kings or aces, right? What's the probability of drawing a king or an ace? Those are mutually exclusive events, right? You can't do both. Like if I have a bunch of different kind of sports balls, right? Picking a basketball or a baseball. Those are mutually exclusive events. They cannot happen at the same time. And so when you have mutually exclusive events, hopefully I've made that clear what a mutually exclusive event is with all the examples, then you're adding the probabilities. Okay, so look at example 2. An experiment consists of spinning the spinner, and the spinner's there. We're either going to land on A, S, C, or E, and they've given us the probability. The probability of landing on A is 0.4, S 0.3, C 0.2, E 0.1. All right. Which of the following pairs of events, E and F, are mutually exclusive? Mutually exclusive means they have no outcomes in common. There we go. So, is that first set where E is ACE and F is CSE, are those mutually exclusive? No, because they have the common outcome of C, right? C is in both of those outcomes. They are not mutually exclusive. Does that make sense? Okay. What about the second one? A vowel and the first 5 letters of the alphabet. Are they mutually exclusive? No, because the first letter is an A, right? And it is a vowel. Okay, a vowel and C, are those mutually exclusive? Yes, because C is not a vowel, right? C is not a vowel, so those are mutually exclusive events. Does that make sense? They have no outcomes in common. All right, now, what is the complement of event A, S? So what is that asking? When it asks what's the complement of AS, it's asking what is the probability that neither one of those is the outcome. So we're adding C and E, that's one option, or we're taking one minus the sum of those probabilities. Got it? And what is the probability of the event the spinner does not land on A? Well, that too is the complement, right? That will be 1 minus the probability that it actually does land on A. So it'd be 0.6. Or, because we know the other options, you could add S, C, and E. Okay, does that make sense? Mutually exclusive events, we're adding. It's one event, one draw, one spin, one flip of the coin. It's one event with no outcomes that overlay one another, right? That overlap. Got it? Okay. There's also independent events. With an independent event, it can be We're asking for the probability of one major event, but it could have two events in it, like flipping a coin twice, right? We're multiplying. Drawing twice, right? We're multiplying. The best example is the flip of a coin. Or the kings and the hearts, right? That I showed you a minute ago. Like drawing a king or drawing a card, we're multiplying. Because it was a king of hearts. Got it? All right, those are independent events. We're multiplying. All right, so on the top of the next page, page 868. With mutually exclusive, typically the word that you hear is or. With independent, typically the word you hear is and. All right, so look at example 3. Example 3 says the probability of winning a certain game is 0.1. Suppose, oh boy, that's pretty low. Suppose the game is played on two different occasions, two games, two events. I'm thinking independent, right? What is the probability of winning both times? That's win. What are we doing? We're multiplying. So it's 0.1 times 0.1. That's the probability of winning both times, which is 0.01. It's very low. It goes lower. The probability of winning both. Since the probability of winning once is very low, then the probability of winning twice
is
even lower. What is the probability of losing both times? Well, you have to think about the complement. What is the probability of losing one game?
0.1.
That's winning.
0.9.
0.9. So losing both would be 0.9 times 0.9. 0.81. That's right. Okay, so this next one. We said that was 0.01. That was win twice, lose twice, 0.81. What about win one, lose one? Well, would that be the complement of these?
Yes.
It would be. So it's 1.00 minus those. It's the complement of those, right? Because our probability has got to add up. It has to add up to 1. And the only options are I win twice, I lose twice, or I win one, lose one. But I could win the first one, lose the second one. I could lose the second, I could lose the first one, or whatever I said the opposite of, right? Whatever that is. Okay. So those are two important concepts. Now, this expected random variable. All right, this is on the top of page 869. A random variable simply assigns a value, a number, to each outcome. Okay, that's all it does. Random value just assigns a value to each outcome. Okay, so we're gonna assign a value to each outcome, and then we're going to find out what the expected, like if I get that one, what is the expected value? It's sort of like the mean. All right, so the easiest way to see this is to walk through examples 4 and 5. Yes. Okay, so I believe they go together. Yeah. All right, so look at example 4. So we're rolling 2 number cubes. All right. A random variable is going to assign the outcome the total of the faces. That's going to be the random variable. The total of the faces on the cubes. okay? So look at the sample space. What's the sample space? 1, 1, 1, 2, 1, 3, 1, 4, and 5, and 6. 2 with all those values, 3 with all those 6 values, and so forth. That is the total sample space. Got it? Just like we did with the cards, right? Well, like if I showed you these cards, and I said, now that we have 2 events, if I showed you these cards, I should write this on the board. And I said, what is the sample space for drawing 2 cards? Okay. Let's just say that, since we're now at more than one. So let's see, I have the 10 of clubs, I have the 9 of hearts, the queen of hearts, the 2 of spades, the 6 of hearts. Okay, I'm going to leave one out, just more to write if I don't. Okay, so what is the sample space? Well, if I'm going to draw 2 cards, all right, well, I could do the 10 of clubs with the 9 of hearts. I could do the 10 of clubs with the, that's wrong, queen of hearts. I was expecting a number. Queen of hearts. I could draw the 10 of clubs with the 2 of spades. I could draw the 10 of clubs with the 6 of hearts, right? And then I'd start over. Then I could do the 9 of hearts with the 10 of clubs. Right? I could draw this one first and that one second. And then so forth, right? That would be the sample space. Okay? And then we might ask, what is the range of the random value? Well, with dice, the smallest that I could roll is 2 ones. So that random variable would be 2, right? The highest value I could roll would be 2 sixes, right? Which is 12. Okay, well, we could do the same thing with cards, right? Saying the queen is, what would the queen be? 12. All right, so the very lowest I could draw is the 2 and the 6, right? So my random variable would go from 8 to 22. Assigning values, right? Does that make sense? Okay. And then it says list the outcomes to which the value 7 is assigned, and they have highlighted that diagonal. That's where all the 7s are. Okay? Expected value is the average of the random variable. Okay, so go to example 5. All right. All right, so what did they do? They wrote the sum of the faces. It's 2 through 12, right? That's the random value. All right, so in the very top, it's that random variable that was assigned, 2 through 12, right? And then they take the probability. So there's only one out of all 36 possible outcomes that we will roll a sum of 2. And so forth. Do you see how they've done that? Mm-hmm. Then they wait. So the expected value is you take that random variable number 2, multiply it by the probability of that outcome, and you add them all up. Do you see that? So they did 2 times 136 plus 3 times 1/8 plus 4 times 1/12. Does everybody see that? So they add them all up. And that tells you if I keep rolling, do you know what's going to show up the majority of the time? A sum of 7. That's what I should expect, is to roll a 7. If I do thousands of events, right? And added up what the outcomes were, I should expect to see the majority of the events roll a 7, a sum of 7. Okay, does that make sense? It's also logical because it's probably the highest probability. All right, so your expected value, what does that take? That takes the random variable that we've assigned to the outcome, right? Multiply it by the probability of that particular event occurring and add all of them up. So it's a weighted probability and tells us what we should expect to happen. We'll look at the lottery. To win $0, look at the percent, 88%. To win $2,500, that is only $2,500, is, I can't even say that number. There's so many zeros in a 4, right? It's 4 millionths or something crazy like that, okay? Look at the expected value to win. This is what, if you buy lottery tickets, you can expect to get 71 cents. You see that? Everybody wants to run out and get a lottery.